Our world appears quite ordinary when viewed from a common perspective. Everything seems ordered and stable. The changing of seasons, birds soaring through the sky, the wind rustling, vehicles cruising along roads, horns blaring, and occasional traffic collisions. This way of perceiving the world is known as the classical perspective. However, there is another way to observe reality, through the lens of quantum physics. The moment you transition from classical to quantum physics, the world takes on a bizarre and fascinating nature. The sea's waves, the birds in flight, the flowing wind, and moving vehicles. All of them are not just in motion but are also simultaneously still. Those who were injured in a vehicle collision are now, surprisingly, both perfectly fine and injured at the same time. This may sound strange, but it is the mind-bending truth of quantum physics. Here, the impossible becomes possible in ways you could never imagine. According to a renowned 20th century scientist, if you place a cat inside a box, it can be both alive and dead simultaneously, a paradox that challenges everything we think we know about reality. I know all this sounds bizarre, but today, we're going to delve into the fascinating world of quantum physics. In this exciting video, we'll introduce you to mind-blowing concepts from Schrödinger's cat to the zero effect that will leave you questioning what's real and what might just be an illusion. For the first time, you may wonder, does this truly happen in the world? Is what we see reality? Or is it some kind of illusion? So, friends, get ready to explore these mysteries with me. Watch this video until the end, because it's going to be an incredible journey. Without further delay, let's dive into the strange and wondrous universe of quantum physics. This field began about a century ago, during a time of rapid progress in science, as physicists proposed groundbreaking theories to help us better understand the nature of reality. In 1900, a scientist named Max Planck introduced a groundbreaking concept that would later be known as the Planck quantum hypothesis. He proposed that energy is emitted and absorbed in discrete packets called quanta. In simpler terms, he explained that energy behaves not only as waves but also as particles. While this idea may seem common knowledge today, it was revolutionary at the start of the 20th century. Back then, energy was believed to exist solely in wave form, and the notion of its particle-like nature sparked significant controversy. Just 5 years later, in 1905, Albert Einstein made his mark on quantum physics. He expanded upon Planck's ideas by explaining the photoelectric effect, demonstrating that light travels in small energy packets, later named photons. This discovery confirmed Planck's hypothesis and earned Einstein the Nobel Prize in 1921. Interestingly, despite his fame for the theory of relativity, Einstein's Nobel Prize was awarded for his explanation of the photoelectric effect. As quantum physics gained traction, more scientists delved into this mysterious field, uncovering phenomena that challenged conventional understanding. In 1924, a new revelation emerged. Not only does energy exhibit wave-particle duality, but matter does too. Fundamental particles like electrons behave both as particles and as waves, a concept proven through countless experiments. In the 1920s, Niels Bohr and Werner Heisenberg introduced a mind-boggling principle. According to their findings, an electron behaves like a particle only when it is observed. When not observed, it exists as a wave. This remarkable insight laid the foundation for the principle of quantum superposition. If this seems strange, here's something even more astounding. According to quantum physics, every fundamental particle in the universe exists in all possible states simultaneously, a reality that defies our classical intuition and continues to captivate the imagination of scientists and thinkers alike. But as soon as we observe it, all those possible states collapse, and the particle chooses to exist as either a wave or a particle. When Bohr and Heisenberg first published this idea, many people laughed at them. The world of quantum physics seemed strange and mysterious compared to the straightforward nature of classical physics. In real life, classical physics concepts work predictably, but when applied to quantum physics, the results were often bizarre and confusing. One of the strongest critics of Bohr and Heisenberg's Copenhagen Interpretation was a famous physicist named Erwin Schrödinger. If you have even a little interest in physics, you've likely heard of him. Rather than criticize their ideas in the usual way, Schrödinger created a thought experiment to scientifically challenge their interpretation. This experiment is now one of the most famous in science and is known as Schrödinger's cat. Here's how it worked. Schrödinger imagined placing a cat inside a sealed box along with a radioactive substance, a radioactive detector, a bottle of poison gas, and a hammer. In the setup, the hammer is connected to the detector, positioned above the bottle of poison. The radioactive substance has a 50% chance of decaying within a certain time. If it decays, the detector will trigger the hammer to smash the bottle, releasing the gas and killing the cat. When the box is closed, we have no way of knowing if the cat is alive or dead. According to quantum physics, before we observe it, the cat is in a state of superposition, both alive and dead at the same time. Only when we open the box and look inside does the superposition collapse, forcing the cat to be either alive or dead, but not both. This strange idea comes from the same principle that says particles in the universe exist in multiple states at once until they are observed. Schrödinger's thought experiment was a creative way to highlight the weirdness of quantum mechanics, where reality behaves very differently from what we experience in everyday life. As I mentioned earlier, when an electron is observed, it behaves like a particle, but when we stop observing it, it acts like a wave. The same strange idea applies to the cat in Schrödinger's experiment. Schrödinger argued that the cat's life or death doesn't depend on whether we observe it. If the cat was dead before we opened the box, it would still be dead after we opened it. Many scientists at that time supported Schrödinger, including Albert Einstein. Interestingly, both Schrödinger and Einstein believed in quantum physics. Schrödinger even created a famous equation that became the foundation of quantum mechanics, and Einstein's work on the photoelectric effect also advanced quantum theory. However, they didn't agree with Bohr and Heisenberg's view that nature behaves randomly. Bohr and Heisenberg claimed that when we observe a particle, the state it chooses is completely random and cannot be predicted. On the other hand, Einstein and Schrödinger thought this was incomplete. They believed there must be hidden variables, unknown factors influencing how particles choose their state. For many years, the debate continued, but by the 1960s, experiments showed there are no hidden variables in quantum physics, proving that Bohr and Heisenberg's interpretation was correct. This doesn't mean Einstein and Schrödinger were entirely wrong. Their questions led to deeper explorations of quantum mechanics. Even today, scientists continue to study these strange behaviors to find more solid explanations. Later, in 1977, two scientists, Vaidyanathan Mishra and George Sudarshan, expanded on the Copenhagen Interpretation by introducing the Quantum Zeno Effect. They discovered that if we continuously observe a particle, we can stop its changes. For example, if we keep watching an electron, it will stay in its particle form and won't switch back to a wave. This shows just how bizarre and fascinating the world of quantum physics can be. By simply observing a particle, we can freeze its state, which is an incredible concept. Even more amazing, this phenomenon has real-world applications. In quantum computers, the Quantum Zeno Effect is used to prevent unwanted changes in data. Similarly, scientists in atomic and particle physics use this effect to control radioactive decay. This shows just how advanced Niels Bohr and Werner Heisenberg's ideas were for their time. Bohr and Heisenberg revealed that the universe is made up of things whose true nature we still don't fully understand. If electrons behave like particles only when observed, it suggests that everything in the universe might exist in wave form when not being watched. Many students of quantum physics arrive at this conclusion. However, that's not the whole picture. Physics is divided into three major branches. Classical physics. It deals with objects of regular size and mass, like cars, airplanes, and humans. Astrophysics. It focuses on very large and massive objects, such as planets, stars, and black holes. Quantum physics. It studies extremely tiny things like electrons, protons, and quarks. Each branch follows different rules. If we try to apply the rules of one field to another, things don't make sense. For example, quantum physics rules don't work for large objects like planets. Scientists believe that to fully understand the universe, we need a theory of everything. This ultimate theory would combine quantum physics, classical physics, and astrophysics into one unified framework, making it possible to explain all the laws of nature. So, which of these three fields of physics fascinates you the most? Let us know in the comments. Until next time, goodbye.